Hello students. Today we're going to do more review topics, a couple of topics today. Piecewise functions is where we're starting, and then we're also going to talk about function operations and function composition. So take a look at number 1 here and number 2. We have a couple of piecewise definitions. This is where you have the function like g of x, f of x, etc. And then you have equals and then an open brace, and then you see multiple pieces. So if you look at the top piece on number 1, think of this as y equals 1/2 x minus 1. So that's going to be a piece of a line. And then the second piece, think of that as y equals 3. That's a piece of a horizontal line. And then the third piece, y equals negative 2x, that's a piece of another line. So we have a piece of a line, a piece of another line, and a piece of another line. And when it's all said and done, it should be a function, so it should pass the vertical line test. And the way I like to graph it is I like to find a couple of points on each line. So I focus on the domain of each piece and get a couple of points. So for the top piece, which I think I'm going to color code them just to make it kind of easier to follow what I'm doing. So I'll go ahead and I'll just use green for the top piece. I want to plug in 0 as an endpoint because that's where it's going to end. It's going to end at 0. We're going to have an open circle there. If I plug 0 into the function, 1/2 times 0 minus 1 is negative 1. Now we need another point because if we have 2 points, we can draw the line. So you can choose whatever other number you want that's less than 0. So I'm going to choose negative 2. 1/2 times negative 2 minus 1 is going to be negative 2. So we're going to start with an open circle at 0, negative 1. We're going to go through negative 2, and keep going. And that will give us that piece. So that should look like a piece of the line y equals 1/2 x minus 1. Okay, moving on to the second piece. The second piece should look like part of the line y equals 3. And notice we have 2 endpoints. So we're going to start at 0. If x is 0, the y value is still 3. And we're going to end at 1. If x is 1, the y value is still 3. The y value is always 3. And because these are less than or equal to signs, we are including the endpoints, so we're going to have closed circles. So we have a closed circle on 0, 3, and a closed circle on 1, 3, and then a line segment in between. And then for the third piece, we're going to use 1 to get our endpoint. So negative 2 times 1 is negative 2. That's going to be an open circle. And then we need some other point that's greater than 1. So maybe I'll just choose 3. Negative 2 times 3 is negative 6. So it's going to go through that point. So start with the end point, 1, negative 2, open circle. Go through the other point and keep going. Okay, now looking at the graph, can you tell that it's a function? It passes the vertical line test, right? Even if you look at x equals 1, whoa, that's a nice vertical line. Okay, it's passing through a point there, but this here is not a point, so that line is only passing through one point. The same thing at x equals 0. It's only passing through that one point where you have a closed circle because the open circle is not a point, it's a hole. By the way, what should you say if you see 3 holes in the ground? Well, well, well. Okay, number 2. We are looking at piecewise function f of x, and the top piece is a rational function. So let's just make a little bit of room and see if we can simplify that rational function. So y equals x squared minus 9 over x plus 3. So it's undefined at x equals negative 3. We're going to expect it to have a vertical asymptote or a hole there. And if I factor the numerator, it's a difference of squares. It factors into x minus 3 times x plus 3. We see that we actually have the same factor that we can cancel from the top and the bottom. So rather than a vertical asymptote, we have a hole at x equals negative 3. So the graph is just going to be whatever it would look like if it was y equals x minus 3 with a hole in it. So we have a line with a hole in it. And we're going to have a piece of that line. So we want to draw that for x equals, or x is anything but negative 3. Okay, So y equals x minus 3 is a line with a y-intercept of -3 and a slope of 1. So we're drawing that for all x values except -3. So we'll put a hole there. And then for the second piece, we have f of x equals 5 when x is -3. So this is actually just a point. It's the point -3, 5, -3, 5. And there's our graph. Sweet. Okay, the next thing I want to do is work backwards. So here's a piecewise function. We're going to determine the domain and range, and then write the piecewise definition. So let's take a look at number 3. Notice how, in terms of the domain, the x values end right there at -6, and then moving our way to the right, it looks like they go through every other possible x value and keep going. So the domain is going to be x is greater than or equal to -6. How about the range? Well, notice that there are only 3 heights for the points. One point is at a height of -5. There are infinitely many points at a height of -2, and there are infinitely many points at a height of 4. So there are only 3 heights. So I'm going to write this as a set with set braces, -5, -2, 4. I can't use an inequality or an interval because that would imply all the numbers in between. Like, we don't want to say the interval from -5 to 4 because that would imply everything in between. We don't want to imply that. Now, how about the piecewise definition? Let's call this whatever we want. We could call it f of x if we want to just kind of keep it simple. There are 3 pieces, so we make room for that. And typically what we do is we work our way from the left to the right. So let's look at this top piece, or excuse me, this leftmost piece. That's a horizontal line at a height of -2, so that's the line y equals -2. So the f of x equals is in place of the y equals, and all we need is the -2, and then we need the domain for that piece. So we're starting at x equals -6, closed circle, going to x equals 2, open circle, so we can say -6 is less than or equal to x is less than 2. Sometimes you'll have the word if in between, like, back here we had the word for in between. Sometimes you have the word if in between. It doesn't matter that much. Now for the second piece, we just have a point. That point is at a height of -5, and that point has an x-coordinate of 2. Now for the piece on the right. This is a horizontal line at a height of 4, so that's y equals 4. So our f of x equals is our y equals. All we need is the 4. And then for the domain, starting at 2, open circle, arrow to the right, so x is greater than 2. Now, if you want to pause and figure out the next one on your own, and then you could resume and we can compare. So for the domain, going from x equals -infinity all the way to 0, but look, open circle at 0, open circle at 0. We're not including 0 at all, and then we're going on from there. So there's a couple of different ways we could write this, and I think I'm going to try to give myself a little more space down here. We could do something like this, -infinity to 0, open brackets, showing we're not including the endpoints, union 0 to infinity, or we could write x is not equal to 0. That's simpler. For the range, notice we have some points at a height of -3, then we jump over a bunch of heights, and then we have points at a height above 0. So we're going to have to make a combination here. We can say we have the numbers y equals -3, or now we can write an interval here or an inequality, doesn't matter. As an interval we can say 0 to infinity. If you were writing an inequality, you could say y is greater than 0. Now for the piecewise definition. Okay, we have a horizontal line, and we did that a couple times on number 3. We also have a slanted line. I'll call this one g of x. So for the horizontal line, that's the line y equals -3. and the domain was x is less than 0. Now for the other line, think about how you get the equation of a line, y equals mx plus b. You need to know the slope m, and you need to know the y-intercept b. We can tell the y-intercept is 0, and you can tell on this one, because the graph is pretty obvious, that the slope is 1. So putting that all together, we have the line y equals 1x plus 0, y equals x. So down in our piecewise function, g of x equals x, and the domain for that piece is x is greater than 0. Okay, so that takes us through the first part of our lesson, piecewise functions. Let's move on to the second piece of our lesson, function operations. So we're going to work with these examples. F of x equals 1 over x minus 3, that's a rational function, and g of x equals square root x. That's a radical function. I guess you could also say it's an algebraic function. And what we're going to do when we say operations, we're talking about things like adding, subtracting, multiplying, and dividing the functions. And notice that in numbers 6, 8, and 10, well actually 5, 6, 8, and 10, we're going to talk about domain. So let's go ahead and start by looking just at f. What's its domain? So you want to ask yourself, what number makes the denominator 0, and exclude that number. So we can say that x cannot be 3. That's the domain of f. What's the domain of g? So because it's a square root function, you know that to get a real output, you have to have a non-negative input inside a square root. So x has to be greater than or equal to 0. Okay, when we find the domain of a combination of these, like the domain of the sum, the domain of the difference, the domain of the product, we have to find the intersection of these two domains. So for number 8, if you're going to find f of x plus g of x, you need the numbers that are in both domains. So the intersection of x is greater than or equal to 0. Here's x is greater than or equal to 0. And x is not equal to 3. Here's x is not equal to 3. Where do they overlap? They overlap from 0 to just before 3, and then after 3. So that would be 0 to 3, closed on 0, open on 3, union 3 to infinity, open on both sides. And that would be the domain of f plus g. That would also be the domain of f minus g, of g minus f. It's also the domain of the product f times g. It would not be the domain of the quotient if we were finding a quotient, because we would have to think about what makes the denominator of our new quotient 0. Okay, to write f of x plus g of x, all we need to do is write 1 over x minus 3 plus square root x, and then if these were functions that we could add together and simplify, we would. Doesn't look like it in this case. And to find f of x times g of x, same idea. Multiply these together. Now what we can do to simplify it is we could just write it as one fraction with square root x on the top and x minus 3 on the bottom. So those are the kinds of things we're talking about if we talk about combining functions or function operations. And the last thing I want to talk about is function composition. Function composition is where you have one function inside another function. So if you're talking about f and g, you might have f of g of x. G is inside f. You might have g of x. F is inside g. Remember the notation for f of g of x could look like that with an open circle there. That's open. Or the notation for g of f of x could look like this, g of f. So we're working with the same functions f and g. Let's find f of g. So g is on the inside. So that means the square root of x is going in place of x. So we're going to do 1 over the square root of x minus 3. Now I'm not going to worry about simplifying that right now or trying to get rid of the radical in the denominator. We'll just leave it at this. Just kind of going over the main idea. How about the domain? Well, you have to kind of think this through. We don't want the denominator to be 0. So we don't want the square root of x to be 3. So that means we don't want x to be 9. Also, just because of the square root itself, x has to be greater than or equal to 0. So x is greater than or equal to 0 and not 9. So that would mean we have 0 to 9, including the 0, not including the 9, union 9 to infinity. And then how about g of f of x? So f is on the inside. So that means that we are taking the whole thing of f of x and substituting it into g in place of x. So that means we have the square root of 1 over x minus 3. How about the domain? Well, we still don't want the denominator to be 0, so x is not equal to 3. But we need the inside of the radical to be positive, or 0. Well, there's no way it can be 0 because the numerator is not 0. So we need the inside of the radical to be positive. We need 1 over x minus 3 to be positive. So if x is a number that's greater than 3, it will be positive. But if x is a number that's less than 3, the denominator will be negative. So how about if we just combine all those ideas together and we have x is greater than 3. Okay. Hopefully that dusted off some of the cobwebs in your brain about those topics. And for your assignment today, we have a few problems out of the book, and we have a piecewise function worksheet. Thanks, everybody.